Please subscribe to support the channel. The universe was born in a blaze of light. Yet what James Webb may have just revealed is a paradox wrapped in darkness, a cosmic monster lurking in the very moments when existence itself was still fragile and new. In the drifting fog of hydrogen, in the cooling afterglow that once painted space with a dim cosmic hush, astronomers have found a whisper of something impossibly large, impossibly early, a black hole so ancient that its presence fractures the timeline we thought governed the birth of everything. It emerges from the faintest strands of light stretched across 13.4 billion years, suggesting that even as the first stars flickered awake, something far more massive was already feeding in the shadows, defying theory, challenging cosmology, and forcing us to confront the unsettling possibility that darkness may have risen just as quickly as light. The universe, only about 350 million years old, was supposed to be a quiet landscape of innocence, a realm defined not by structure but by potential, by delicate gas clouds drifting through expanding space as gravity slowly coaxed them into the first generations of stars. This was an era before metals, before complex chemistry, when the cosmos knew only hydrogen, helium, and the soft pull of gravity knitting the earliest galactic seeds into being. Stars in this epoch were colossal, short-lived beacons, their deaths marking the very first opportunities for black holes to form. And according to the rules we believed governed cosmic evolution, those black holes should have begun as tiny remnants, barely more massive than the stars that birthed them, growing only through slow accretion or rare mergers. Yet in this tender infancy, as galaxies were still learning how to exist, evidence now hints at something grotesquely out of scale. A black hole that seems to have reached the mass far beyond what this young universe should have allowed. It is as if the cosmic nursery was haunted by a giant that should not have been born yet. A gravitational presence assembled far too fast, disrupting the quiet story we once told about how galaxies began. This paradox sits at the heart of the mystery. How could such immense mass gather so swiftly, in an era when the universe had barely had time to take its first breath? What emerges next is the instrument that made such a paradox visible at all. The silent, gold-mirrored eye suspended far beyond the distortions of Earth's atmosphere, patiently gathering the most ancient light ever recorded. For decades, astronomers knew the early universe was there, just out of reach, hidden behind wavelengths stretched so far by cosmic expansion that optical telescopes like Hubble could no longer see them. The first galaxies were not just faint. Their light had been pulled into the infrared, dissolved into a spectrum only a new kind of detector could reveal. And so the James Webb Space Telescope was born, not merely as an upgrade, but as a reimagining of how we look into the past, a machine crafted to peel back epochs that had never been witnessed by human eyes. Its architecture is built with purpose, a segmented mirror collecting photons older than Earth, older than the Sun, older than most of the galaxies we know. Beneath that mirror lie instruments designed to dissect and analyze light in ways that feel almost forensic, splitting it into spectral signatures that act like cosmic DNA. Webb's infrared capabilities allow it to see through the opaque dust that once obscured the earliest phases of galactic birth. The telescope does not simply capture light, it interprets it, stretching faint signals into readable patterns, turning whispers from the dawn of the cosmos into full decipherable sentences. Without this sensitivity, the glow from galaxies like GHZ2 would have remained lost in the background, drowned out by the universe's own expansion. As Webb peers deeper, it does something no predecessor could do. It reaches across almost the entire age of the universe and brings back snapshots from its cradle. The early universe is not merely distant, it is dim, diffused, and swaddled in primordial fog. Only a tool capable of catching the lowest energy photons, one so stretched they barely cling to the electromagnetic spectrum, can hope to unveil it. Webb does this by cooling its instruments to near absolute zero, reducing noise until even the faintest ancient signal becomes detectable. The result is unprecedented clarity. Structures that once appeared as vague smudges now reveal patterns, textures, even chemical fingerprints. The telescope has unlocked a corridor of time we could previously only imagine, a path into the epoch when galaxies were flickering into existence for the very first time. And in that corridor lies the first hint that something extraordinary was waiting for us. When astronomers first analyzed deep-field images from Webb, they were struck by how crowded the early universe seemed. Far more galaxies appearing far earlier than any model had predicted. These galaxies were too massive, too luminous, too quickly assembled. The expectation had always been that the early universe built slowly, but Webb's early findings hinted at a cosmos racing ahead when physics told us it should still be fumbling with basic building blocks. This discovery alone set the stage for deeper surprises, because if galaxies were forming faster than expected, then whatever lurked in their centers might be evolving faster than we thought possible. In this way, the potential discovery of the earliest supermassive black hole is not just a scientific curiosity, it is one of the first fruits of Webb's radical new vision. The telescope's spectrographs reveal details that no image alone could show: delicate emission lines, traces of ionized gases, and the unmistakable fingerprints of extreme radiation. These spectral whispers are the kind of signals that older telescopes would have blurred or missed entirely, but Webb captured them with surgical precision, allowing astronomers to ask questions that would have been unthinkable even a few years ago. Instead of debating whether such early monsters existed, scientists found themselves confronting evidence that they might have been there all along, hiding behind wavelengths we could not previously observe. The truly transformative aspect of Webb's capabilities is not just that it sees farther, it sees differently. Infrared vision reveals not only what objects look like, but what they are made of, how they behave, how they evolve. In the case of GHZ-2, it allowed astronomers to read signs of intense ionization that hinted at an engine far more powerful than young stars alone. Without Webb, this faint, distant galaxy would be an anonymous dot in the abyss. With Webb, it becomes a window into one of the deepest mysteries in cosmology: the possibility that black holes, massive and ancient, emerged alongside the very first structures in the cosmos. In a sense, the telescope has become a time machine, not metaphorically, but literally, because every photon it collects began its journey before our planet existed. Through its instruments, we are not just observing history, we are witnessing origins. And as Webb continues to scan the dark, its ability to detect anomalies like the one in GHZ-2 reminds us that the universe is far stranger, far more dramatic, and perhaps far more violent in its youth than any model dared to predict. The discovery is not an endpoint, but an invitation, a promise that the closer we look, the more the cosmos will challenge every assumption we thought we understood. What emerges out of Webb's deep field images is a kind of cosmic apparition, a dim and distant blur of light that should not, by any conventional expectation, exist in the form we see it. GHZ-2 is not bright in the way quasars are bright, nor sharp in the way modern galaxies are sharp. It is faint, delicate, almost ghost-like, as though the universe itself only barely had time to sketch its outline before sending its light across 13.4 billion years of expanding space. Yet within that faintness lies a remarkable defiance of time. GHZ-2 appears as it was when the universe was only about 350 million years old, a moment so close to the Big Bang that cosmic structures should still have been fumbling into coherence. And yet here it is, not a chaotic mist, not a loose association of half-formed stars, but a galaxy that seems startlingly mature for such a young epoch. Its light, stretched into the infrared by the accelerating expansion of the universe, carries within it the story of a place that should barely have existed. Galaxies during this era were expected to be tiny, primitive sparks, clusters of newly ignited stars with barely any organization. Yet GHZ-2 contradicts that expectation by displaying an unexpected level of development. Not only does it show signs of active star formation, but it also appears to possess the mass and structure of an object that has somehow evolved faster than the universe should have allowed. This alone is enough to raise questions, but GHZ-2 goes beyond being simply too early or too massive. It radiates subtle clues through its spectrum, clues that point toward energy processes that should not have been possible at that time. The galaxy seems to be whispering that something enormous, something powerful, something deeply unanticipated lies at its core. This mystery deepens when we consider just how improbable GHZ-2's existence is within our current cosmological framework. The early universe was dominated by cold gas and dark matter halos, gradually condensing under gravity. Star formation was turbulent, inefficient, and easily disrupted by radiation from the first supernovae. Galaxies should have taken hundreds of millions of years to assemble enough mass to look anything like GHZ2. Yet here it stands, a compact but fully functional system, exhibiting signs of intense internal energy. This leaves astronomers with an uncomfortable set of possibilities. Either the universe formed its first galaxies far faster and more efficiently than predicted, a scenario requiring major revisions to our understanding of early structure formation, or GHZ2 is not simply a galaxy, but the host of something far more dramatic, a hidden powerhouse shaping its development from the inside. What makes the galaxy feel like a ghost is not only its distance, but its silence. It sits at the threshold of what our telescopes can detect, its image blurred by the sheer stretch of spacetime. But its spectral signature carries a pulse, faint but unmistakable, that signals unusual conditions. When Webb gathered GHZ2's light and astronomers unraveled its spectrum, they found patterns that seemed too energetic for a normal young galaxy. The chemical fingerprints, especially the high ionization lines, suggested that something within GHZ2 was pumping enormous quantities of radiation through its surroundings. For such intense ionization to occur, one would expect the presence of stars far hotter than any typical population in such an early galaxy. Yet even extreme stellar nurseries cannot fully account for the strength of the signals detected. It's as though GHZ2 has a hidden engine generating radiation at a level its age and mass should not permit. Complicating matters further is just how little time the universe had granted GHZ2 to form. Stars take millions of years to coalesce from gas, and galaxies take even longer to stabilize and grow. The presence of a structured, luminous galaxy at this redshift already strains theory. But GHZ2 does more than strain it. It stretches it to near breaking. If this galaxy has a powerful central engine, as early data suggests, then that engine must have assembled with astonishing speed. We are forced to consider that the birth of structure in the universe may not have been the slow, orderly buildup we once imagined. Instead, the dawn of time may have been a frenzy of rapid formation, gravitational collapse, and violent energy release. GHZ2 becomes a symbol of that frenzy, a relic of a cosmos far more dynamic than the smooth, gradual evolution our models once described. There is a poetic tension to GHZ2's existence. It is both faint and powerful, both distant and immediate. When we look at it, we are not merely seeing a faraway galaxy. We are witnessing a moment when the universe was still learning how to make galaxies at all. We are reaching into a chapter of cosmic history so early that even the slightest hint of complexity becomes revolutionary. GHZ2 is not just a data point, it is a challenge, a provocation. It stands as evidence that the early universe may have been capable of feats we have not yet learned to explain. Its ghostly profile might be fragile, but the questions it raises are seismic. And the mystery is only just beginning, because the next step is to ask what exactly produced those spectral clues, the high-energy whispers that hint at a hidden source of intense radiation buried within this ghost of the cosmic dawn. The deeper we move into GHZ2's spectral fingerprints, the more its faint light begins to speak, not loudly, not with the blinding flare of a quasar, but with subtle, razor-thin signals that carry the unmistakable tension of something powerful hidden within. Astronomers study these signals the way archaeologists handle ancient inscriptions, carefully, methodically, knowing that every emission line is a message from a world that no longer exists. And the spectrum of GHZ2 holds a message written in ionized gas, in wavelengths stretched by 13.4 billion years of cosmic expansion, a message that should not be possible for a galaxy so young. The most startling feature is the presence of intensely strong C4 lambda 1548 emission, a line produced when carbon atoms have been stripped of 3 electrons, a condition requiring radiation fields far more extreme than any ordinary star-forming region could produce in the infant universe. This is not the signature of gentle starlight. This is the mark of something violent. In ordinary galaxies, especially modern ones, this kind of high ionization radiation is associated almost exclusively with powerful central engines. active galactic nuclei, supermassive black holes feeding at rates high enough to blast our surroundings with intense ultraviolet and X-ray radiation. But GHZ2 is not supposed to host such an engine, not in this era, not in this cosmic moment. The first stars had only just begun to shine, galaxies were only beginning to assemble their gas. The universe had not yet formed heavy elements in abundance, and supernovae had barely started spreading those elements through space. For triply ionized carbon to appear so strongly, something must have been creating an energy environment wildly disproportionate to the expected conditions of this epoch. The presence of such a line is like seeing a glowing coal buried beneath fresh snow, a clue that something hot, intense, and persistent lies hidden below the surface. Yet the spectral puzzle deepens further when we examine what is missing. If GHZ2 housed a typical active galactic nucleus, we would expect to see more than just high ionization emission lines. We would expect the signs of the AGN continuum, the broad UV excess, the distinct X-ray luminosity, the unmistakable fingerprints of a supermassive black hole operating at full throttle. But GHZ2 does not reveal these classic traits. There is no roaring quasar blaze, no X-ray spike pointing unequivocally to a feeding black hole, no high-power jets carving through the surrounding gas. Instead, the spectrum is quiet, too quiet for comfort, and that silence makes the residual high-energy lines all the more unsettling. If a black hole truly hides inside GHZ2, it is not behaving like any AGN we fully understand. It is smothered, cloaked, or perhaps existing in a mode we have never witnessed before. This strange mismatch, intense ionization paired with muted AGN indicators, forces astronomers into unfamiliar territory. Could the early universe have supported exotic stellar populations capable of producing such radiation? Theoretical models of population 3 stars, the first stars composed entirely of primordial hydrogen and helium, suggest they could have been enormous, possibly hundreds of times the mass of the Sun. Their surface temperatures would have been blisteringly high, capable of generating extreme ultraviolet radiation. But even these titans may not fully explain the observed strength of the C4I line. The signal appears too strong, too persistent, too tightly linked to conditions typically associated with black hole activity. And population 3 stars, if present, should produce additional spectral behavior, helium lines, unique chemical imprints that GHZ2 does not clearly exhibit. Another possibility is that GHZ2 represents an entirely new mode of early galaxy radiation, something transitional, something that blurs the line between stellar and AGN processes. The early universe may have hosted hybrid systems, dense stellar clusters feeding compact black hole seeds, giving rise to intermediate energy outputs that mimic certain AGN-like features without producing the full quasar signature. These transitional phases are poorly understood, partly because no telescope before JWST had the sensitivity to detect them. The result is a kind of scientific vertigo, a sense that we are observing something we do not yet have the vocabulary to describe. To interpret GHZ2's spectral whispers is to acknowledge how limited our previous view of the early universe was. If these high ionization lines are truly the fingerprints of a hidden black hole, then GHZ2 becomes a revelation, evidence that supermassive black hole seeds may have formed far earlier and more aggressively than any model had predicted. If instead, they are the signatures of unknown stellar processes or some exotic starburst phenomenon, then our understanding of early stellar evolution is incomplete. Either way, the spectrum is not just data, it is a challenge, a disruption, a crack in the theoretical foundation that demands explanation. And the crack grows wider when we consider the context. This is not just any galaxy. GHZ2 exists at the threshold of cosmic dawn, in an era so close to the universe's birth that even modest complexity should be rare. These high ionization lines found in its spectrum should not exist without a powerful driver. Yet the driver hides from us. For every clear feature Webb reveals, another vanishes into ambiguity. The puzzle is elegant, haunting, and deeply provocative. It whispers of forces at work long before they should have awakened. Which leads inevitably to the next question. If the spectrum of GHZ2 hints at an unseen engine, Then what is the nature of that engine, and how could something so immense have taken hold so early in time? At the center of GHZ2, hidden beneath layers of ionized gas and wrapped in a silence that should not belong to something so powerful, lies the most compelling explanation for its spectral strangeness: a black hole. Not the small, stellar mass kind that forms from collapsing stars, but an actively feeding engine, a gravitational furnace drawing in surrounding material and releasing torrents of energy as it devours its host galaxy. The clues align like constellations: the triply ionized carbon, the unusual radiation intensity, the subtle signatures of heating that exceed what early stars could produce. Everything points toward an active galactic nucleus, the unmistakable hallmark of a black hole in the act of feeding on its host galaxy's primordial gas. And yet, GHZ2 defies the expectations that typically make such detections clear. It behaves like a predator whose footsteps are visible, whose breath is warm, but whose body is concealed behind shadow. Ordinarily, an actively feeding black hole reveals itself with unmistakable force. The accretion disk, a swirling torrent of gas heated to millions of degrees, emits a harsh, bright continuum across ultraviolet, optical, and X-ray wavelengths. Jets of relativistic particles may shoot from its poles, carving channels through surrounding space. Radio emissions flare. Infrared signatures spike. In the modern universe, these features make AGNs unmistakable, even when they are partially obscured or hidden behind clouds of dust. But GHZ2 offers only half the script. The black hole's fingerprints appear as faint but undeniable traces, while its voice, the high-energy roar of X-rays, is missing. This absence complicates the story. A dormant black hole would not ionize surrounding gas to this degree. Yet an active black hole should produce strong X-ray signals that Webb or other observatories would detect. GHZ2 instead presents a paradox: the radiative imprint of a feeding giant without the luminous body we expect to see. One explanation is that the black hole is heavily obscured, smothered by dense clouds of gas that trap most of its radiation. In the early universe, galaxies were thick with neutral hydrogen, chaotic star-forming regions, and clumpy reservoirs of primordial material. A young black hole, newly ignited and drowning in infalling gas, might simply be too buried to reveal its full power. Its radiation could be reprocessed, absorbed, and re-emitted as spectral lines rather than broad continuum light. Such buried AGNs exist even in the modern universe, hidden monsters whose presence is revealed only through the ionization they imprint on their surroundings. GHZ2 might represent an early, extreme version of this phenomenon. The black hole could be feeding at an extraordinary rate, but suffocated beneath its own growth, wrapped so tightly in infant cosmic matter that only the highest energy photons manage to escape. Another possibility is that GHZ2's black hole is not behaving like any we have documented. The earliest black holes may have operated in a transitional mode, smaller than typical AGNs but larger and hungrier than stellar remnants. These intermediate mass black holes could feed in bursts, flickering between visible and invisible phases, illuminating their surroundings only sporadically. In this scenario, GHZ2 might be caught in a moment between breaths, revealing just enough radiation to ionize carbon, but not enough to shine in familiar wavelengths. If true, Webb has captured a phase of black hole evolution that has long been theorized, but never directly observed. Yet the question lingers: could something else produce these conditions? Could massive, pristine population 3 stars mimic the spectral imprint of an AGN? Some argue yes, but even these theoretical giants struggle to match the sheer intensity required for triple ionization of carbon on such a scale. Others propose exotic star clusters, dense pockets of radiation created by thousands of young, hot stars forming simultaneously. But these explanations often require assumptions that contort our understanding of early star formation. It becomes a battle between two unlikely possibilities: a black hole that appears too early, or stars that behave in ways no star population is known to behave. And in that comparison, the black hole remains the cleaner explanation, not because it is simple, but because it aligns most directly with the observed features. A feeding black hole naturally produces the ionization GHZ2 displays. It naturally sits at the center of a galaxy. It naturally shapes its surroundings with violent radiation. The pieces fit, even if the complete picture remains blurred. The universe often hides its most powerful forces behind incomplete signatures, behind clues that reveal enough to provoke discovery, but not enough to grant certainty. GHZ2 is one of those clues, a whisper that may mark the birth of the first supermassive black hole we have ever glimpsed. If that whisper is real, then the next question becomes inescapable. How could a black hole grow so large, so quickly, in a universe barely out of its origin? If GHZ2 contains a black hole, then its formation must have been radically different from the slow, steady process we assume for modern black holes. The early universe had no time for patience, and to explain this temporal impossibility, we must explore the two dueling birth stories that aim to explain how such cosmic monsters first came to be. The mystery of GHZ2's hidden engine forces us to confront one of the deepest questions in astrophysics. How do the universe's most massive black holes come into existence in the first place? Even in the modern cosmos, supermassive black holes, millions to billions of times the mass of the Sun, present an evolutionary puzzle. They sit at the hearts of galaxies like gravitational monarchs, ancient, powerful, and seemingly inevitable, yet their origins remain uncertain. And when we turn our gaze toward the early universe, when time itself was barely taking shape, the problem becomes far sharper. If a black hole truly lurks within GHZ2, feeding and shaping its host galaxy only 350 million years after the Big Bang, then we must ask, how did it get there so quickly? What seeds could have grown into such a monster in so little time? Two competing narratives attempt to answer this question, each with its own assumptions, predictions, and tensions. The first is a familiar one, the light seed story. In this scenario, the earliest black holes are simply the corpses of the first massive stars. These stars, known as population 3 stars, formed out of pristine hydrogen and helium and lived short, dramatic lives. When they died, they collapsed into black holes perhaps 30, 50, or even 100 times the mass of the Sun. These light seeds, according to the traditional timeline, slowly accreted gas over hundreds of millions of years and sometimes merged with one another to grow further. Over vast stretches of cosmic time, through steady feeding and occasional violent encounters, they became the supermassive black holes that anchor galaxies today. But this incremental, patient growth runs directly into a temporal wall when applied to GHZ2. Light seeds growing at realistic rates simply do not have enough time to reach supermassive scales so early. Even if they fed at the maximum rate allowed by physics, the Eddington limit, they would still struggle to reach the sizes required to produce the kind of ionization observed. The math is brutally clear. At 350 million years after the Big Bang, a black hole born from the death of a first-generation star would be too small, too young, too starved of fuel to shape an entire galaxy's spectral profile. To bridge the gap between theory and observation, one would have to assume feeding rates several times higher than the Eddington limit, or invoke exotic, untested mechanisms that would push the boundaries of known physics. Light seeds, though elegant the idea is, buckle under the weight of GHZ2's implications. The second storyline, the heavy seed scenario, provides a more dramatic but potentially more realistic explanation for GHZ2's spectral whispers. In this model, black holes do not begin as the remnants of stars. Instead, they begin much larger, forming directly from the collapse of massive gas clouds. Under extremely specific early universe conditions, unusually high gas densities, low metallicity, and intense radiation fields suppressing star formation, an entire cloud of primordial gas could collapse under its own gravity to form a black hole of perhaps 10,000 or even 100,000 solar masses. These heavy seeds emerge fully armed, far larger than any stellar remnant, and starting from such enormous mass, they can grow into supermassive scales dramatically faster, even within the short window of cosmic history available at redshift 14. This heavy seed model has long been attractive but difficult to confirm. It requires fine-tuned environments and specific conditions that we have never observed directly. It has remained until recently a theoretical possibility lurking in simulations and speculative papers. But if GHZ2 truly contains a black hole behaving like an AGN, then the heavy seed model leaps from speculative to plausible. A gas cloud collapsing directly into a black hole could give rise to exactly the kind of early energetic signature we see. A young black hole with enough mass to ionize carbon and shape its galaxy's environment, even at such a primitive epoch. GHZ2 becomes not merely an observational curiosity, but a potential fossil of heavy seed formation, a window into a process we have never witnessed but have long suspected. And yet, confirmation would not simply validate one theory over another. It would fundamentally rewrite our understanding of cosmic dawn. If heavy seeds existed, the early universe must have been a place far more chaotic and conducive to rapid collapse than previously imagined. Massive gas clouds would need to exist undisturbed long enough to bypass star formation entirely, a difficult feat in a time when star birth was rampant. Radiation fields would need to be precisely tuned to suppress fragmentation. Density fluctuations would need to align perfectly. For heavy seeds to form in substantial numbers, the early universe would have required a kind of exquisite balance, one that feels almost unnatural in its precision. But if that balance did occur, even briefly, then black holes may have been born alongside or even before the first galaxies. They may have played a foundational role in shaping their hosts, seeding structure, regulating growth, and accelerating the development of the cosmic web. In such a timeline, black holes are not endpoints of stellar evolution. They are core components of cosmic architecture, gravitational scaffolding present from the beginning. This possibility raises its own haunting question. If heavy seeds were common, where are their descendants today? Did they grow into the supermassive giants we see in modern galaxies? Did they shape the Milky Way's own central black hole? Or did most of them die, merge, or dissipate in the violent turbulence of early cosmic evolution? GHZ2 opens the door to these questions, but does not resolve them. It offers only the faint light of a distant galaxy, and the silent suggestion that somewhere within it, a black hole may have been born not of death, but from direct collapse. And that suggestion leads us toward uncertainty, toward alternative explanations, toward skeptics who argue that something other than a black hole could produce the spectral clues we see. The debate is far from settled, and the next step requires confronting the shadows and doubts that still swirl around GHZ2's identity. The further astronomers peer into GHZ2's faint spectral signature, the more they feel the presence of uncertainty pressing against the edges of the discovery. The high ionization emission lines may whisper of a black hole, but whispers can be misleading, especially when they originate from an era of the universe we have never directly observed before. Skepticism is not just expected, it is essential. And so, scientists begin by confronting the most sobering possibility that GHZ2's spectral behavior might not come from a black hole at all, but from something far more exotic, far more difficult to categorize, or perhaps far more mundane in the context of cosmic infancy. One of the leading counterarguments is that GHZ2 could be powered by extraordinary stars, stars unlike any that exist today. The early universe was home to the hypothetical population 3 stars, the first generation of stars ever formed, forged entirely from primordial hydrogen and helium. These stars are thought to have been monstrously massive, possibly hundreds of solar masses, burning hotter and brighter than anything in the modern cosmos. Their ultraviolet radiation would have been fierce, capable of ionizing gas to degrees that modern stellar populations cannot match. In theory, a dense cluster of such stars could produce spectral lines resembling those of an active galactic nucleus. If GHZ2 were undergoing an extreme, rare burst of population 3 star formation, it might mimic the high-energy signatures typically associated with the black hole. But this explanation comes with its own complications. Population 3 stars are expected to leave distinct chemical fingerprints, patterns of helium and metal pore emission lines that should imprint themselves onto the spectrum. Many of these signatures are either absent or ambiguous in GHZ2's data. Additionally, population 3 stars burn out quickly, often within a few million years. For GHZ2 to exhibit such intense ionization, it would need an enormous number of these stars forming merely simultaneously, in a burst so intense that it strains theoretical star formation models. It is possible, but it demands a level of synchronized vigor that even the most optimistic simulations struggle to support. Another alternative is that GHZ2 might harbor supermassive stars, gargantuan hypothetical behemoths formed from direct gas collapse before fragmentation occurs. These stars, if they existed, would radiate strongly enough to produce extreme ionization, perhaps even rivaling the output of a low-level active nucleus. Some theoretical models suggest these stars could arise in precisely the environments required to suppress fragmentation and avoid forming normal star clusters. But just like the population 3 explanation, this idea requires finely tuned conditions, and the lack of distinctive chemical lines make it difficult to argue that supermassive stars alone could account for the spectral features Webb detected. A more subtle alternative is that GHZ2 might represent a kind of hybrid system, a turbulent, metal-poor starburst environment where multiple overlapping processes create unusual ionization conditions. The early universe was not chemically mature, and galaxies during this epoch likely behaved differently from the galaxies we see today. Gas density, temperature distribution, and star formation efficiency may have created environments capable of producing spectral signatures we do not yet fully understand. Perhaps GHZ2 is showing us a new mode of early cosmic behavior, one where the line between stellar and non-stellar energy production blurs. This possibility, while fascinating, also throws us into deeper ambiguity. If the early universe produced radiation environments unlike anything observed in the local cosmos, then interpreting GHZ2 becomes a complex puzzle without a clear solution. Skeptics also highlight what is missing from the evidence. If GHZ2 hosts a black hole, why do we not see strong X-ray emission, the typical hallmark of an active galactic nucleus? Even a heavily obscured black hole should produce some X-ray photons capable of penetrating surrounding gas. The lack of such detection raises eyebrows. Perhaps the black hole is so deeply buried that even X-rays cannot escape. Perhaps its feeding mechanism is intermittent, captured by Webb in a low luminosity phase. Or perhaps there is no black hole at all, and the ionization arises from a completely different source. Compounding the uncertainty is the fact that the analysis of GHZ2 spectrum has not yet undergone formal peer review. The findings were posted on arXiv, a repository for scientific preprints, meaning the conclusions have not yet faced the full scrutiny of the astrophysical community. In this early stage, the data are vulnerable to reinterpretation, further analysis, and potential correction. Astronomers know all too well that spectral lines can be misidentified, that early universe galaxies can behave unexpectedly, and that extraordinary claims require extraordinary evidence. GHZ2's nature remains an open question, an intriguing possibility, but not a confirmed reality. In the shadow of these doubts lies a deeper truth about cosmic exploration. Every discovery at the edge of the observable universe forces humility. The early cosmos is an alien landscape, filled with physical conditions we cannot recreate, and stellar populations we have never seen before. The ionization lines from GHZ2 could indeed signal the earliest known black hole, but they could also represent a phenomenon we have not yet imagined. The caution is not meant to diminish the wonder, but to preserve the scientific integrity that ultimately deepens it. Yet, even as doubts accumulate, one idea remains difficult to shake. If GHZ2 is not the first black hole, it may still be the earliest one we can see. Our tools reveal only what light permits. The universe is filled with darkness, both literal and conceptual, and many early black holes may lie beyond our detection limits, too faint or too buried to illuminate the cosmos in ways we can capture. GHZ2 sits right at the threshold of our observational frontier, teasing us with ambiguity, reminding us that the boundary between discovery and uncertainty is often razor thin. And so we are led toward a sobering reflection. Even if GHZ2 is merely the first visible candidate, what does that imply about the countless others that may remain hidden? What secrets lie beyond what we can detect? In the haze of uncertainty surrounding GHZ2, one truth emerges with remarkable clarity. Whatever it is, whatever engine drives its strange radiation, it stands as the earliest such object we have ever been able to observe. That distinction carries enormous weight, because the cosmos is not simply revealing a curiosity, it is exposing the extreme limits of what our instruments can presently perceive. GHZ2 sits at a distance so vast, in an era so primordial, that it is perched at the very edge of what the James Webb Telescope can resolve. The light that reaches us began its journey not long after the first atoms formed. And if a potential black hole signal appears in this faint, fragile halo of ancient photons, then we must consider the implications of seeing only the brightest, least obstructed examples of a much larger unseen population. GHZ2 may not be the universe's first black hole, but it might be the earliest whose voice is loud enough for us to hear it through the suffocating depths of time. This distinction is profound because cosmic visibility is never an unbiased window. We do not see the universe as it was, we see only the parts bright enough, clear enough, or unobstructed enough to survive a journey of 13.4 billion years. Countless young galaxies in the early universe were likely smothered in dust, or too faint to register even on Webb's exquisitely sensitive detectors. Early black holes, if they existed in abundance, might have been drowned in thick veils of gas, producing little light capable of escaping. Some might have fed quietly, hidden behind the dense hydrogen fog that blanketed the early cosmos during the era before reionization fully cleared the intergalactic medium. This means GHZ2's visibility is an accident of cosmic geometry, a stroke of observational luck, and perhaps a sign that there are many more similar objects lurking just beyond our reach. This realization forces an uncomfortable but necessary humility. When we detect the earliest black hole candidate, we are not identifying the first in any absolute sense. We are identifying the first one the universe has allowed us to see. The cosmos is vast, and its opacity in the early epochs means enormous swaths of history remain hidden or distorted. What Webb detects is the brightest tip of structures that likely form a much larger, more complex population. GHZ2 might be exceptional to us, but in reality, it may have been common, merely one among millions of early galaxies hosting black hole seeds. The only reason it stands out is that the right photons slip through the expanding fabric of space with just enough energy to reach our detectors.
Our view of the universe is thus not complete. It is a filtered, fragile glimpse shaped by physics, distance, and technological limitations. Consider how we see the present-day universe, with telescopes across every wavelength capturing everything from X-rays to radio waves, revealing black holes and multiple modes of emission. But in the early universe, most wavelengths cannot escape the dense, neutral gas filling space. X-rays get absorbed, optical wavelengths scatter. Only a narrow sliver of infrared light survives. We're looking through a cosmic keyhole, not at the whole room, but at the fraction of it illuminated in just the right way. GHZ2 is the figure standing closest to that keyhole. Beyond it may be countless others we will not detect for decades, perhaps centuries. This awareness reshapes our interpretation of GHZ2 in a fundamental way. Rather than treating it as an outlier, we must consider it as a sample, the earliest detectable representative of a population that may have existed on a scale we have never imagined. If GHZ2 harbors a black hole, then many other early galaxies might have done the same. If GHZ2 formed rapidly, then rapid formation might have been normal. If GHZ2 contains the spectral fingerprint of an early active nucleus, then such nuclei may have been widespread, shaping the earliest stages of cosmic evolution long before galaxies fully matured. The absence of evidence elsewhere is not evidence of absence. It is often a sign of observational limits. And this line of thinking carries a deeper, more philosophical implication. Our cosmic history, the timeline we teach, the models we build, the narratives we construct is shaped not by what happened, but by what we are able to see. Light defines our understanding. Darkness obscures it. The earliest black holes may have been hidden behind fogs of gas or trapped in galaxies too dim to illuminate the universe. GHC2 might be a survivor, a rare moment where ancient photons navigated the labyrinth of cosmic expansion without being swallowed by dust or scattered into oblivion. It is a beacon not because it is unique, but because it endured. This realization leaves us with a sobering form of cosmic humility. For all our knowledge, for all our instruments, for all our theories, the early universe remains mostly invisible. GHZ2 does not close the book on cosmic dawn. It opens it. It tells us that what we are seeing is only a sliver, a glimpse, a fragile hint of a much larger story unfolding behind curtains we cannot yet part. And if this faint galaxy, barely formed, can harbor such a powerful signature, then the true history of the universe may be stranger, darker, and more densely populated with early black holes than we ever expected. This leads naturally to a broader, unsettling question. If the early universe was filled with objects like GHC2, then its history, its formation, its evolution, its very narrative may need to be reconsidered entirely. What GHC2 ultimately forces us to confront is the growing realization that the early universe may not have been the clean, orderly, slowly assembling cosmos we once envisioned. Instead, it may have been a roiling cauldron of rapid collapses, chaotic star formation, violent radiation fields, and gravitational giants taking shape with astonishing speed. The more we probe this epoch, the more the familiar narrative dissolves, giving way to something richer, wilder, and far more difficult to predict. GHC2 feels like a clue dropped into the simmering chaos, a reminder that the early universe was not a pristine nursery, but a turbulent forge boiling with energy and potential. If a black hole truly lurks within it, then its existence is not an anomaly. It is a symptom of a deeper cosmic disorder that our models have yet to capture. At the dawn of time, gas clouds did not drift gently into structure. They collided, compressed, and fractured under the influence of dark matter halos, whose gravitational pull sculpted the first filaments of the cosmic web. In these dense pockets of gas, stars ignited in violent bursts, radiating ultraviolet light that began to erode the neutral hydrogen fog around them. Galaxies did not grow peacefully. They cannibalized one another, merged, tore themselves apart, and reassembled into new configurations. The early universe was a battlefield of gravity and light, and within this battlefield, black holes could have acted as accelerants, influencing everything from gas turbulence to star formation rates. If GHZ2 contains a massive black hole seed, then its host galaxy may have been shaped by that presence from the very beginning. A feeding black hole, even a small one by modern standards, pumps vast amounts of energy into its surroundings. It heats gas, disrupts star formation, and can cause entire regions of a galaxy to light up or collapse. In the present-day universe, AGN feedback can quench star formation or regulate it with remarkable precision. In the early universe, where galaxies were fragile, unstructured systems still learning to exist, the influence of a black hole would have been even more profound. It might have accelerated the collapse of surrounding gas, creating pockets of intense star formation, or it might have blown out gas entirely, reshaping the galaxy before it had truly formed. This feedback loop becomes even more interesting when we consider that the early universe had very different physical conditions than the universe today. Gas was more abundant, less chemically enriched, and far easier to compress under gravity. A black hole forming in such an environment could grow rapidly, fed by dense streams of pristine hydrogen. Instead of the slow, regulated growth we observe in modern galaxies, early black holes may have entered phases of runaway accretion, doubling their mass in short cosmic bursts. GHZ2 may represent one of these moments, a snapshot of a galaxy undergoing radical transformation under the influence of a newly formed gravitational titan. But if this is true, then the standard models of early galaxy evolution begin to unravel. We have long assumed that galaxies emerged first, creating black holes only after stars had lived, died, and collapsed. But what if the opposite is true in many cases? What if black holes formed simultaneously with their galaxies, or in some instances even preceded them? Heavy seed black holes, born from direct gas collapse, can act as gravitational centers that accelerate galaxy formation around them. Rather than black holes forming within galaxies, galaxies may have grown around black holes. This inversion of cosmic causality challenges a century of astrophysical thinking and forces us to reassess how structure emerged in the first place. The presence of such early black holes would also reshape our understanding of reionization, the epoch when ultraviolet light from the first stars and galaxies cleared out the hydrogen fog filling the universe. If black holes were numerous and active during this period, their energy output could contribute significantly to reionizing the cosmos. This would alter the timeline of when and how the universe transitions from opaque to transparent, reshaping models that rely on the brightness of early galaxies to explain this process. Perhaps faint obscured black holes did much of the work previously attributed to stars alone. GHC2 hints at this possibility, that the universe's great transformation was not driven solely by starlight, but by a combination of light and shadow, creation and gravitational destruction. These implications ripple outward through every branch of cosmology. Simulations of early structure formation, previously calibrated to produce small galaxies and modest black holes in the first few 100 million years, may need to expand their parameters. Star formation models may need to account for extreme radiation environments and unpredictable feedback patterns. Dark matter simulations might need to integrate earlier and more massive central black holes to predict the formation of large-scale cosmic structures. GHC2 becomes more than a single galaxy. It becomes a mirror, reflecting the inadequacies of our current models, urging us to reimagine the early universe not as a place of gentle origins, but as a boiling, vibrant, fiercely creative epoch. There is a kind of thrill in this uncertainty, a reminder that the universe is not obligated to match our expectations. The early cosmos may have hosted phenomena that do not exist today, processes we cannot yet conceptualize, and formations that challenge every neat boundary we build into our simulations. GHC2 whispers that our picture of cosmic dawn is incomplete, that we stand at the shoreline of knowledge gazing into a sea of unknowns far deeper than we realized. The soup of the early universe is thicker, more complex, more volatile than any simple model suggests, and every anomaly Webb reveals adds another ingredient to that primordial broth, enriching it with mystery. In this soup of uncertainty, one thing becomes clear. GHC2 does not merely call for tuning existing theories, it demands their transformation. It suggests a universe that grew not calmly, but explosively, not linearly, but chaotically, driven by forces that shaped stars, galaxies, and black holes in ways we have only just begun to decode. And this leads naturally to a sobering thought. If GHC2 is not alone, if other early black hole candidates exist, then the puzzle is far larger than a single galaxy. Which leads us directly to the next realization. GHC2 may be just one piece of a pattern emerging from Webb's increasingly surprising discoveries. As the data from JWST continues to accumulate, something remarkable begins to emerge, a pattern. Faint at first, then increasingly persistent, like constellations slowly taking shape in a once empty sky. GHC2 might be the most extreme example yet, but it is not the first hint that the early universe was teeming with objects far too massive and too luminous for their age. Webb's earliest deep field observations shocked astronomers by revealing galaxies that seemed impossibly mature only a few 100 million years after the Big Bang. Some had stellar masses rivaling modern galaxies. Others glowed with such intensity that they defied every prediction about how fast stars could form in the cosmic dawn. And then came the even stranger signals, the signatures of active galactic nuclei at redshifts corresponding to 500 or 600 million years after the Big Bang. These were black holes, already millions, even billions of solar masses, existing long before current models said they should. Before Webb, discoveries of ancient quasars at redshift 7 or 8 were considered groundbreaking. These quasars, detected by surveys like the Sloan Digital Sky Survey and observed in more detail by Hubble and ground-based telescopes, already posed a serious challenge to the light seed model. They were simply too massive, too soon. But those objects, as shocking as they were, still appeared hundreds of millions of years after the epoch now under scrutiny. GHC2 pushes the timeline back dramatically into an era so early that it essentially rewrites the boundaries of what early universe even means. But Webb's data suggests it is not alone in doing so. Other galaxies at redshifts 10, 11, and even 13 have shown anomalously bright features, strange spectral lines, or suspiciously compact structures that hint at the possible presence of black hole seeds. The emerging pattern is subtle but unmistakable. The early universe shows signs of rapid, extreme, and highly efficient assembly. Galaxies formed earlier than expected, stars formed faster than expected, and now it appears that black holes may have formed earlier and perhaps more often than anyone had anticipated. GHC2 stands out because of the clarity and extremity of its high ionization lines, but in truth, it is part of a growing collection of galaxies whose properties defy the neat, gradual timeline once favored by cosmologists. Webb has returned a universe that looks less like a calm dawn and more like a cosmic firestorm, brilliant, violent, and wildly productive. This cluster of anomalies forces us to reconsider fundamental assumptions about how matter behaved in the universe's first few 100 million years. If numerous galaxies show signs of early black hole activity, then black hole seeds must be forming rapidly and under a wide range of conditions. It is no longer enough to imagine a few rare heavy seeds arising in perfectly tuned environments. Instead, we may need to consider the possibility that direct gas collapse, runaway accretion, or other exotic formation channels were common in the early cosmos. The pattern suggests that the mechanisms that built the first massive black holes were not outliers. They were standard ingredients of early cosmic evolution. The universe may not have stumbled into these monsters occasionally. It may have produced them routinely. Another intriguing aspect of Webb's findings is how normal many of these early galaxies appear. They do not all resemble blazing quasars or heavily distorted merger remnants. Instead, some look surprisingly calm, compact, and well-formed, as if their central black holes grew alongside their stellar populations in a synchronized, mutually reinforcing cycle. This contradicts long-standing beliefs about galaxy black hole coevolution, which assumed that black holes gained dominance only after galaxies had already assembled a significant fraction of their stars. If black holes were emerging early and often, they may have played a primary role in guiding galactic growth, serving as gravitational anchors or feedback engines shaping the young universe. This pattern also raises the question of whether we have been fundamentally misreading the cosmic timeline. Perhaps star formation was far more efficient than expected. Perhaps dark matter halos collapsed more quickly or more violently. Perhaps gas could funnel into galactic centers with extraordinary speed under the unique conditions of the early universe. Whatever the case, GHC2 and its companions fit into a broader narrative that is emerging, the realization that our models underestimate the pace and power of early cosmic formation. The discoveries accumulate like evidence in a mystery that is far from solved: a galaxy too bright, a quasar too massive, a spectral signal too energized, a black hole candidate too early. These anomalies are no longer isolated. They are clustering into a story that challenges the foundational assumptions of cosmology. GHC2 may be one of the earliest data points, but it strengthens what the others were already hinting at, that the early universe was not merely surprising, but systematically so. And this brings us to one of the most profound implications of this growing pattern. If multiple early galaxies show signs of rapid black hole growth, then perhaps GHC2 is not an anomaly at all. Perhaps it is a representative of an entire hidden population we have only begun to uncover. Which leads us naturally to the next question.
one that pushes speculation to its grandest scale. If these early black holes are more common than we thought, how many remain hidden? And what does that imply about the universe's first billion years? If GHZ2 is merely one visible piece of a much larger cosmic pattern, then the most unsettling possibility begins to take shape. The early universe may have been filled with black holes that we simply cannot see. Not rare, not accidental, not marginal, but abundant, woven into the very structure of cosmic dawn like dark nodes anchoring the first luminous webs of starlight. The thought reshapes the narrative entirely. Instead of envisioning a universe where black holes appear only after the first massive stars have lived and died, we are confronted with the possibility that these gravitational giants may have been forming alongside galaxies, or even before them. GHZ2 becomes less of an isolated anomaly and more of a lighthouse showing us where to look next, hinting at a population of primordial monsters hiding in the shadows of the early cosmos. This hidden population, if real, would imply that the universe's earliest epochs were dominated not simply by the birth of stars, but by the interplay between creation and collapse, between radiant light and gravitational darkness. Many black holes in this era would have been deeply buried in gas, their signatures masked by dense neutral hydrogen that blanketed the universe prior to reionization. Their accretion light may never have escaped. Their energy may have been smothered into the infrared or trapped entirely. These early black holes could have existed in staggering numbers, altering the structure of the universe without leaving behind the bright beacons we associate with modern active galaxies. GHZ2 may appear visible only because conditions happen to allow its radiation to slip through the cosmic fog, like a single flare rising above a vast unseen battlefield. If such a population existed, then the implications stretch far beyond black hole formation alone. Early black holes could have profoundly influenced the birth of galaxies themselves. They could have acted as seeds around which gas condensed more rapidly, accelerating galaxy formation. Instead of galaxies giving rise to black holes may have been catalysts for the earliest galactic structures. Their gravitational pull could have drawn matter inward with extraordinary efficiency, creating compact, intense star-forming regions. Their radiation and feedback could have shaped the chemical and thermal state of the intergalactic medium, perhaps even contributing significantly to reionization. This is not the universe we once imagined, a place where stars lead and black holes follow. It is a universe where darkness and light grow together, where collapse and emergence are inseparable, where gravitational monsters may have been present at the dawn of cosmic time. And the idea becomes even more provocative when we consider the possibility that some of these hidden black holes could be primordial in origin, not born from stars, not born from gas clouds, but formed directly from density fluctuations in the early universe, only seconds or minutes after the Big Bang. These primordial black holes, if they exist, could have served as seeds for early galaxy formation, or merged repeatedly to create heavier and heavier early black hole populations. While still speculative, the existence of an entire population of primordial seeds would offer a simple explanation for why GHZ2 and potentially many other early galaxies appear to host black holes far too massive for their age. Instead of relying on improbable accretion histories or perfectly tuned direct collapse events, we could simply acknowledge that some black holes were born before galaxies themselves, relics of the universe's first moments. The more we explore this possibility, the more fascinating the implications become. If early black holes were common, then the cosmic web's earliest nodes might have been shaped not by dark matter alone, but by a synergy between dark matter and black hole gravity. The first massive structures could have formed faster and on larger scales than standard simulations predict. The dawn of the universe might have been a far more active environment, with countless small black holes glimmering faintly in regions we have no hope of observing directly. In this speculative landscape, GHZ2 becomes our first confirmed glimpse into what may be a much larger hidden ecosystem. Its spectral signals may represent nothing more than the brightest and clearest example of a process occurring all across the early cosmos. Black holes forming, feeding, merging, influencing, and perhaps dominating the dynamics of their young host galaxies. This forces us to rethink our assumptions about chronology.
We may have pictured the early universe backwards. Instead of the story being first stars, then galaxies, then black holes, it may be that the true narrative was first collapse, then black holes, then galaxies. And that reversal carries enormous philosophical weight. It implies that darkness, gravitational collapse, the seeds of destruction, was not merely an after effect of creation. It may have been present at the universe's first dawn, emerging alongside the first sparks of light. Black holes, in this interpretation, are not latecomers. They are co-authors of cosmic history, shaping structure as it formed, guiding the growth of galaxies, and perhaps even influencing the earliest phases of cosmic expansion. If this hidden population exists, then it means GHZ2 is not an outlier. It is a clue, a messenger, a faint torch illuminating an entire generation of ancient gravitational titans still buried beyond the reach of our technology. And if that is true, then the stakes of confirming GHZ2's identity grow dramatically, because doing so would require us to redraw the timeline of the universe itself. If GHZ2 truly harbors a black hole so early in cosmic history, then the implications ripple outward through every corner of astrophysics, tearing into the foundation of the cosmic story we thought we understood. The stakes are nothing less than the rewriting of the universe's earliest chapters. Our models of galaxy formation, our assumptions about black hole growth, our simulations of structure formation, all of it would require revision. Cosmology has long relied on a timeline built on gradualism. Small fluctuations form stars, stars form galaxies, galaxies grow larger, and only after enough time passes do black holes emerge from stellar deaths and grow into the giants we see today. But GHZ2 threatens to flip that sequence, suggesting a universe in which black holes were not the concluding punctuation of cosmic evolution, but one of its opening acts. If so, the entire chronology of the first billion years needs to be reevaluated. A black hole at only 350 million years after the Big Bang suggests that formation pathways are faster, more efficient, and more extreme than any model has predicted. It implies that massive structures may have taken shape in a universe that was still hot, dense, and turbulent, environments so dynamic that runaway collapses could have become common. In such a scenario, galaxies may not have leisurely assembled from star clusters merging over time. Instead, they may have collapsed rapidly around gravitational wells formed by early black hole seeds. This means our timeline of when galaxies should have grown to certain masses or when they should have developed recognizable structures becomes unreliable. JWST's startling images have already revealed too big too soon galaxies. GHZ2's potential black hole expands this pattern into the realm of the extraordinary. If early galaxies formed faster and black holes formed earlier, then the relationship between the two may be fundamentally different from what we have assumed. Instead of black holes evolving within galaxies, they may have co-evolved with them, exerting influence from the earliest stages. Their feedback, the energy they release while feeding, could have shaped star formation rates, redistributed gas, and influenced the overall architecture of their host galaxies. This feedback, known to regulate galaxy growth in the present-day universe, may have played an even more significant role when galaxies were tiny, fragile structures just beginning to emerge from primordial gas. The earliest chapters of cosmic evolution could have been a feedback-driven battleground where nascent galaxies fought against the overwhelming energy of their central engines. The stakes grow even higher when we consider cosmological simulations. For decades, astrophysicists have built elaborate numerical models showing how structure forms from the interplay between dark matter, gas, and radiation. These simulations are calibrated to match observations of the cosmic microwave background, large-scale galaxy surveys, and the behavior of galaxies in the modern universe. But if the early universe hosted black holes far earlier and more frequently than predicted, then these models are missing a key ingredient. They would need to incorporate new physics, more rapid gas collapse, earlier fragmentation, more efficient accretion, or radically adjust assumptions about star formation and feedback. A universe seeded with early black holes behaves differently from one that waits for stars to create them. Even the dark matter narrative may feel the tremors of such a discovery. If early black holes formed preferentially in dense regions of dark matter halos, then their presence could influence how these halos evolved, merging more quickly or forming structures earlier than expected. Some theories even suggest that dark matter itself might help channel gas into dense enough configurations to initiate direct collapse black hole formation. If GHZ2 represents such a process, then the stakes extend beyond baryonic physics and into the mysterious realm of dark matter behavior. The implications reach beyond astrophysics into the philosophy of cosmology. Our story of the universe has always leaned toward light. Stars ignite, galaxies form, and black holes represent the dramatic but secondary punctuation marks in the cosmic saga. GHZ2 challenges that hierarchy, presenting a universe in which darkness, collapse, gravity, hidden mass may have been a formative force from the beginning. It forces us to ask whether black holes are byproducts of star formation or fundamental agents that shape the universe's earliest architecture. If the latter, then the universe's narrative becomes far more complex, a tapestry woven equally from illumination and annihilation. And beyond all theoretical recalibrations lies the existential weight of what such a discovery means for humanity's understanding of origins. If the universe formed its first gravitational monsters nearly as soon as physics allowed, then the cosmos was born into violence, not tranquility. Creation was never gentle. The first luminous structures emerged alongside voracious forces capable of swallowing light itself. The earliest eras of cosmic history were sculpted not just by expansion and cooling, but by devouring, collapsing, and gravitational domination. This realization brings with it an unsettling beauty. It suggests a cosmos that is far more dynamic and dramatic than our earlier models portrayed. A universe that rushed headlong into complexity, creating and destroying with equal intensity. And if GHZ2's black hole is real, then we must face the reality that many more such gravitational giants may lie in the unseen depths of cosmic dawn, forever beyond our observational reach. Which leads naturally to the questions that haunt every scientist studying the early universe. If this black hole exists, how did it form? What conditions allowed it to arise so early? And how common were these ancient monsters? The possibility that GHZ2 contains a black hole so impossibly early in cosmic history opens a doorway, not into answers, but into a vast chamber of questions that echo with uncertainty. These are not small questions. There are questions that stretch across the entire discipline of cosmology, scraping at the edges of physics, challenging the assumptions we've built our models upon. They linger like cosmic ghosts, persistent, unyielding, demanding confrontation. And each one forces us to admit how much we still don't know about the universe's earliest moments. The first question is the most obvious and the most profound. How did the seed of such a black hole form? If GHZ2 truly houses a massive feeding black hole, then the universe must have had mechanisms to create these objects long before stars had time to evolve and collapse. Was it a direct collapse event, a colossal cloud of pristine hydrogen imploding under its own gravity without ever forming stars? Or was it something even more exotic, an entirely new formation channel we haven't yet theorized? Could turbulence, dark matter, or primordial density fluctuations have created gravitational wells strong enough to form black holes outright? The early cosmos may have been capable of physics we have yet to understand, operating in regimes so extreme that our current models barely scratch the surface. Closely tied to that mystery is the question of what environmental conditions allowed such a seed to grow so rapidly. Even if a heavy seed formed with an initial mass of tens or hundreds of thousands of suns, it still needs fuel. Accretion requires dense reservoirs of gas, stability, and paradoxically, just enough turbulence to funnel material inward. Was GHZ2 sitting in an unusually dense pocket of the early universe? Did it form in the center of a dark matter halo primed for runaway collapse? Or did some unknown feedback mechanism accelerate its growth in ways we've never considered? The feeding process is just as mysterious as the formation process, and both must be reconciled with the brutal scarcity of time available at such early epochs. Then comes the haunting question of how common these early black holes truly were. Is GHZ2 an outlier, a statistical oddity caught in a rare cosmic alignment? Or is it a mere representative of a vast, unseen population? If the latter is true, then the early universe may have been packed with black hole seeds, some visible, others invisible, many lost forever behind the thick fog of primordial hydrogen. And if they were numerous, then they must have played a foundational role in shaping early galaxies. Did these black holes merge over time, growing into the supermassive monsters we observe in the centers of modern galaxies? Are the behemoths in galaxies today, including Sagittarius A at the heart of the Milky Way, the evolutionary descendants of these early seeds? The connection between past and present becomes an intricate cosmic lineage, one we have only just begun to trace. This leads inevitably to an even deeper question. What does the existence of such early black holes tell us about the nature of matter, energy, and gravity in the first moments after the Big Bang? The universe was denser, hotter, and more volatile, conditions under which physics may have played by rules we no longer observe. Perhaps there were ephemeral forces at work, briefly accessible during that early epoch, that allowed black holes to form more easily. Or perhaps quantum fluctuations imprinted tiny variations in density that later collapsed into gravitational wells. The birth of these early monsters could reveal hidden truth about the fabric of space-time itself, truth we have not yet uncovered because our telescopes have only just begun to glimpse that era. The questions do not stop there. We must also ask, how did these early black holes interact with their surroundings? Did they ignite star formation or suppress it? Did they carve out cavities in gas clouds? Did they contribute to reionization, helping to clear the fog that once smothered the young universe? Each possibility leads to a different picture of cosmic dawn, with black holes playing roles we have barely started to quantify. And perhaps most unsettling of all is how many of these early black holes still exist today. Did they merge into larger black holes? Did they die in violent events we have no record of? Or are some of them still wandering the universe, hidden within dwarf galaxies or drifting rogue through intergalactic space? These questions cascade into one another, forming a chain of unknowns so vast that even the most advanced telescopes can only scratch the surface. GHZ2 illuminates a single point on a map we have not yet drawn, a map of early cosmic evolution filled with blank spaces, question marks, and uncharted pathways. It forces us to acknowledge that the universe is far stranger than the tidy models we've created to describe it. And perhaps the most haunting question of all is not scientific but philosophical. What does it mean that the universe, in its earliest and most fragile moments, formed objects capable of swallowing light itself? Creation and destruction, light and darkness, expansion and collapse, all present from the beginning. GHZ2's soft spectral whisper is not a conclusion. It is an invitation, a quiet, ancient voice saying, "Keep going. Look deeper. You do not yet understand what this universe truly is." And it is that tension, the dance between discovery and uncertainty, that leads us toward the next stage in this unfolding cosmic mystery. The long, careful process of waiting for scientific confirmation. The breath held across the astronomy community as we await the data that could strengthen or shatter this extraordinary claim. The thrill and terror of a discovery like GHZ2 is that it arrives wrapped in uncertainty, a fragile signal caught at the very edge of our observational capabilities. And now the scientific community must enter the most difficult phase of all, the long, quiet stretch between possibility and confirmation. This is a period defined not by the fireworks of discovery, but by the careful discipline of patience, scrutiny, and relentless verification. GHZ2 sits on archive for now, unreviewed, its claims untested by the full rigor of peer evaluation. It is a whisper waiting to be either amplified or dissolved. And in that waiting, the entire field holds its breath. Science moves slowly here because it must. Extraordinary claims demand extraordinary proof, and nothing about GHZ2 fits comfortably within the boundaries of ordinary. The first step in this journey involves deeper observations, more photons, cleaner spectra, higher resolution. The current data, while tantalizing, remains limited, drawn from early JWST surveys not specifically tailored to expose AGN behavior at such incredible distances. Targeted follow-up campaigns will be needed, using Webb's most sensitive spectrographs to check and recheck every emission line, confirm their energies, and ensure there are no misinterpretations or calibration errors. Every spike in the spectrum must be examined with care, because in objects this distant, noise and cosmic variance can play tricks on even the most experienced observers. Researchers need repeated observations, taken under different conditions, different instrumental modes, and ideally from complementary telescopes to make sure GHZ2 signals are real and not artifacts of data reduction or cosmic interference. But verifying a black hole so far away also requires looking beyond JWST. Astronomers will turn to telescopes across multiple wavelengths to search for the supporting signs of AGN activity. X-ray emissions from the accretion disk, radio signals from jets or compact cores, sub-millimeter signatures from heated dust possibly illuminated by a growing black hole. The Atacama Large Millimeter Submillimeter Array, ALMA, may help detect the presence of hot dust or gas flows. Chandra or future X-ray observatories may be able to catch even the faintest X-ray photons escaping GHZ2's primordial environment. If these observations reveal consistent footprints, even small, faint echoes of a feeding black hole, then the case strengthens. If they remain silent, the mystery grows only deeper. Silence can mean obscuration or absence, and distinguishing between the two is a scientific challenge so demanding it may take years to unravel. Meanwhile, theorists must refine their models. They will simulate galaxies at this redshift under a variety of conditions, with heavy seeds, with light seeds, with no seeds at all. They will push the boundaries of what the codes can compute, testing whether extreme starburst or exotic stellar populations could produce emission lines that mimic AGN signatures. They will ask whether carbon could be ionized to the degree observed by previously unknown mechanisms, or whether some expected feedback process might temporarily elevate ionization without invoking a black hole. These simulations are not a formality. They are essential. They determine whether the claim is physically plausible, whether it aligns with cosmological constraints, and whether it fits into any coherent narrative of early structure formation. And then comes the peer review, the slow, meticulous dialogue between authors and experts who examine every detail, every method, every assumption. They will challenge interpretations, cross-check calculations, question uncertainties, and demand evidence. This is where claims get sharpened or shattered. Even scientists eager for the discovery must approach it with skepticism. They know too well the history of premature claims, spectacular anomalies that later dissolve under scrutiny. They understand that the earliest epochs of the universe are treacherous terrain, plagued with noise, distorted by cosmic expansion, and filled with processes we still barely understand. The scientific method demands rigor, not excitement, and GHZ2 now waits in that crucible. But beneath the careful caution lies a quiet tension. What if further data contradicts the initial findings? What if the emission lines weaken under closer analysis? Or what if GHZ2's radiation comes not from a black hole, but from an exotic stellar population we have not yet modeled properly? It wouldn't be the first time an extraordinary claim fizzled into the mundane. And yet, what if the opposite happens? What if more data strengthens the signal, revealing the unmistakable footprint of a feeding black hole at cosmic dawn? What if this object stands strong beneath the weight of scrutiny, confirming that a massive black hole existed less than 500 million years after the universe began? The stakes were enormous, and the suspense is palpable. Every new observation, every new dataset, every new simulation will either push GHZ2 closer to confirmation or nudge it toward reclassification. This liminal state, this breath held across the scientific community, is where science lives between discovery and truth. It is the longest breath in astronomy, the moment between seeing and knowing. And in the silence of that waiting, one cannot help but feel the weight of the universe pressing in, whispering that whatever the answer is, it will reshape our understanding of the cosmos. Because if GHZ2 is confirmed, if this black hole is real, then the next chapter is nothing less than a reimagining of the universe's origin story,
a story in which darkness rises alongside light, shaping creation rather than waiting for it. If GHZ2's black hole is ultimately confirmed, the universe's origin story will need to be rewritten from the ground up. It would signify the moment we recognize that the cosmos was never a gentle place, easing itself into complexity, but a realm where gravitational giants emerged not at the end of stellar evolution, but at the very dawn of creation. In this revised narrative, black holes are no longer the byproduct of dying stars. They become co-founders of structure, entities that shaped galaxies from the moment those galaxies began to coalesce. Confirmation would mean that cosmic dawn was not a soft illumination of first starlight, but a braided emergence of radiant brilliance and devouring darkness, each influencing and sculpting the other. The most profound result of such confirmation is the acceptance that supermassive black holes did not need hundreds of millions of years to grow. Instead, they could appear fully formed, or nearly so, from mechanisms beyond the standard astrophysical script. A confirmed early black hole would force cosmologists to acknowledge that heavy seeds were not rare accidents, but likely central components in the architecture of early galaxies. Gas clouds collapsing directly into black holes, with masses tens of thousands of times greater than the Sun, would cease to be speculative constructs and instead become essential agents of cosmic evolution. These seeds could then feed rapidly in dense early environments, ballooning into supermassive monsters at a pace that was once thought impossible. Such a narrative redefines the entire cosmic landscape. Galaxies at cosmic dawn would no longer be simple star-forming systems, but complex interactive structures where central black holes actively influence their development. Their intense gravitational pull and fierce radiation could have regulated the flow of gas, triggering bursts of star formation or suppressing it. They could shape the morphology of early galaxies, contributing to the compactness and rapid growth that JWST has already revealed. Instead of galaxies nurturing black holes into existence, galaxies and black holes might have nurtured each other, forming symbiotic systems that evolved in tandem, not sequentially. This has profound consequences for understanding reionization, the epoch when ultraviolet light cleared the fog of neutral hydrogen that filled the universe. Historically, reionization has been attributed to the first stars and galaxies. But if early black holes were common and active, they may have contributed a substantial portion of the high-energy radiation needed to reionize the universe. Their energetic output, especially if obscured, could have heated and ionized their surroundings far more efficiently than stars alone. Reionization would become not just the triumph of starlight, but a joint effort between stellar radiation and black hole-driven ionization, a process shaped equally by the emergence of light and the force of gravitational darkness. With GHZ2 confirmed, simulations of early cosmic structure would need to be recalibrated. Theories of star formation, feedback cycles, gas dynamics, and dark matter behavior would all be affected. Models would have to integrate early, massive black holes as active agents in shaping their surroundings, not optional additions. This ripple would spread outward, influencing our understanding of galaxy clusters, cosmic filaments, and the very emergence of the large-scale structure we observe today. Early black holes may have functioned as gravitational anchors around which matter condensed, accelerating the formation of galaxies and, perhaps, even enhancing the clumpiness of the early cosmic web. Even the formation of modern supermassive black holes would take on new meaning. Instead of growing slowly through mergers and accretion over billions of years, many of the black holes we observe today might trace their lineage directly back to ancient heavy seeds like the one hypothesized in GHZ2. Sagittarius A, the black hole at the Milky Way center, might not be a quiet remnant of intermediate-era processes, but a descendant of one of the first-generation black holes, shaped by eons of mergers and steady feeding. If this lineage can be mapped backward, then GHZ2 becomes not only a discovery about the past, but a bridge connecting the earliest black holes to the ones still influencing the structures of galaxies today. This new cosmic narrative also alters the philosophical fabric of how we view the universe. If darkness, in the form of black holes, was present alongside or even before the earliest light, then creation itself becomes a more complex, dualistic process. The universe was not born in purity and order, but in a kind of gravitational tumult where luminous structures and shadow-born giants emerged simultaneously. Light did not rise alone, it rose intertwined with forces bent on swallowing it. And yet, paradoxically, these forces helped sculpt the luminous universe we see today. Darkness and light were not adversaries, but co-creators. The confirmation of GHZ2's black hole thus becomes a transformative moment in cosmology. Not only does it birth a new narrative for the early universe, but it also forces us to confront the possibility that our understanding of cosmic origins has been incomplete, that we have underestimated the role of black holes in shaping the cosmos at every scale. With confirmation, the story of the universe becomes richer, stranger, and vastly more dramatic. Creation becomes a dance between collapse and emergence, between luminous energy and gravitational hunger. And once we accept this new narrative, we're left to consider how the ripples of such ancient processes extend all the way to the present, into the galaxies around us, and even into our own cosmic neighborhood. If GHZ2's black hole is real, then its existence doesn't remain confined to the distant past. It sends ripples forward through billions of years, touching the cosmic structures we see today, and perhaps even influencing the very galaxy we inhabit. The idea that a black hole could have been active so early forces us to consider whether the massive black holes anchoring modern galaxies are not simply long-term products of cosmic evolution, but descendants of ancient seeds formed when the universe was still in its infancy. In this light, the Milky Way's central black hole, Sagittarius A, becomes not a quiet object buried in the present, but a final chapter in a lineage that may stretch all the way back to the cosmic dawn. Instead of imagining modern galaxies as late bloomers that slowly grew their central giants, we must entertain the possibility that those giants were present from their youth, or even before the galaxies themselves took shape. If black holes like the one in GHZ2 formed early and influenced their host galaxies, then the echoes of their presence should still be visible in the large-scale structure of the universe. Black holes act as gravitational anchors, drawing gas into dense configurations that eventually ignite star formation. Over time, they can regulate this process by heating or expelling gas, sculpting their galaxies from within. In the early universe, this feedback would have been even more dramatic. Galaxies were small, fragile, and easily disrupted. A feeding black hole could shape the distribution of gas throughout the galaxy, determining where stars formed, how quickly the galaxy grew, and even whether it survived early gravitational turbulence. This influence could propagate across cosmic time. Galaxies built around early heavy seed black holes may have grown faster, merged more frequently, or developed different structures than galaxies lacking such early black hole anchors. Over billions of years, these early differences compound, affecting not only the shapes and sizes of galaxies today, but the distribution of matter across the cosmic web. The great filaments of galaxies stretching across the universe may partially owe their structure to gravitational seeds planted during the universe's earliest moments. Even on the smaller scale of individual galaxies, echoes of early black hole activity may persist. The tight correlations between black hole mass and galactic properties, such as the M-sigma relation linking black hole mass to stellar velocity dispersion, could be relics of this ancient coevolution. These relationships are surprisingly precise, as if black holes and galaxies grew in a synchronized dance. The presence of early black holes shaping galaxies from the inside out provides a natural explanation for these correlations. If black holes were influencing galactic evolution from the very start, then of course the two would be intimately connected billions of years later. GHZ2, therefore, becomes a fossil embedded in cosmic history, a marker of a process that continued across epochs, repeating itself over and over until it formed the galaxies we see today. It becomes even more profound when we consider the stars we see in the night sky. Many of them, perhaps most of them, formed in galaxies whose histories were shaped by early black holes. The structure of the Milky Way, the spiral arms, the distribution of clusters, the timing of star formation bursts, may all bear the faint imprint of ancient gravitational forces that acted when the universe was just beginning.
Even the existence of the Sun, a relatively ordinary star in a quiet corner of the galaxy, might be part of a cosmic story influenced by black hole activity billions of years earlier. If ancient black holes seeded galaxies, then our own existence is in some small way tied to those primordial engines. This also means that when we look up at the night sky, we are not just looking at a tapestry of stars, we are looking at a relic of a cosmic narrative in which black holes have been present from nearly the beginning. The serene beauty of the stars masks a deeper truth. Many of the galaxies scattered across the universe bear the fingerprints of ancient gravitational forces, shaping their growth long before they reached maturity. The universe did not evolve in a smooth cascade of starlight, but through the interplay of radiance and collapse, of illumination and shadow. Modern galaxies are the quiet descendants of a universe once roaring with energetic feedback, rapid growth, and the gravitational influence of newborn black holes. As we uncover more of these faint echoes from the past, a remarkable picture starts to emerge, one in which every galaxy, including our own, carries within it the memory of cosmic dawn. And as we trace these echoes backward, we inevitably confront the limits of what we can see, and the realization that the universe's earliest history is dominated not by visibility, but by invisibility, a hidden realm of objects and events forever beyond the reach of light. For that leads us directly into the next truth. Much of the universe's early history is not simply unknown, it is unknowable. The more we uncover about GHZ2 and its possible black hole, the more we are reminded of a sobering truth. The universe's history is mostly invisible to us. Not metaphorically, literally. The earliest epochs are shrouded behind walls of physics that light cannot penetrate. What we see through telescopes like JWST is not the full story, not even a substantial portion of it, but a thin slice carved out by the narrow pathways where ancient photons happen to slip through. GHZ2's faint glow, stretched across billions of years, is an exception, a rare survivor of cosmic obscuration. For every galaxy we detect at that epoch, countless others likely remained drowned in primordial fog or dimmed by dust. And the black holes that may have shaped them? Many would have been completely hidden, their radiation absorbed or scattered long before it could begin its journey towards us. This realization reframes our understanding of the early universe. We tend to imagine cosmic dawn as a brightening, stars flickering on, galaxies forming, light slowly piercing the darkness. But the truth is far more complex. Most of the universe at that time was opaque, smothered in neutral hydrogen that absorbed ultraviolet light with ruthless efficiency. Early black holes, if they fed aggressively, would have released intense radiation that struggled to escape their surroundings. In this thick, foggy environment, their accretion disks would not blaze across the cosmos the way modern quasars do. Instead, their energy would be muffled, drowned, transformed into faint infrared signatures, or lost entirely. Entire populations of early black holes could exist without producing any detectable radiation at all. They would be gravitationally present, cosmically influential, and observationally invisible.
Adding to this invisibility is the sheer immensity of distance. The farther back we look, the more stretched, weakened, and degraded light becomes. Every photon we receive from GHZ2 is a survivor of unimaginable odds, having traveled across a universe expanding faster and faster over time. As light stretches into the infrared and beyond, much of it slips outside the range of even Webb's instruments. Some wavelengths never reach us due to cosmic redshifting, and others are absorbed by intergalactic gas long before they could escape. The early universe therefore exists to us in fragments, incomplete, discontinuous, speckled with anomalies and silences. For every object that breaks through, there may be thousands whose signals were extinguished across cosmic time. This makes the earliest black holes especially difficult to detect. Even if they were common, even if they played a major role in shaping galaxies, we would see only the brightest and least obscured examples. A hidden population, massive, ancient, and fundamental, could lie just beyond our observational threshold.
These black holes might sit in faint dwarf galaxies, too dim for current technology to resolve. Or they might occupy regions where dense gas obscures the faint trickle of light that escapes. Some may have merged into larger black holes long ago, their early histories erased. Others may have drifted through intergalactic space, stripped of their galaxies by violent gravitational encounters. The reality is unsettling. Our entire reconstruction of cosmic history is based not on what happened, but on what light survived to tell the tale. And in the early universe, light was fragile. Much of it never reached us, and much of the cosmos's earliest activity remains veiled in silence. GHZ2 is therefore not just an object of interest, it is a reminder of the vastness of what we cannot see. The universe's first stars, its first galaxies, its first black holes, most of them may forever remain unobserved. We detect only the brightest anomalies, the rare moments when cosmic conditions aligned in just the right way. This raises profound philosophical questions. How much of the universe's past lies beyond recovery? How much of the true cosmic story is lost because photons never reached us? What events shape the universe in ways we will never detect? Our telescopes give us glimpses, but these are like tiny windows into a massive cathedral. The majority of the structure remains hidden in shadow. The earliest black holes may be key architects of cosmic history, but most of them exist in a domain where light cannot reveal them. It forces us to confront the humbling truth that the universe does not exist for us to observe. We receive what it permits us to receive, not what we wish to see. GHZ2's whisper is significant not just because of what it tells us, but because it illuminates how much remains unspoken, how many secrets lie beyond the boundary of detection. The early universe is a realm built on darkness, both literal and conceptual. And if these ancient black holes were shaping galaxies long before the universe became transparent, then the true history of creation is encrypted within shadows we may never fully decode. Which brings us naturally to the next frontier, the hopeful, forward-looking question of how science will continue pushing against these limits, and what new tools and missions might finally unveil the hidden population of early black holes long concealed behind the veil of cosmic dawn. If GHZ2 is the first hint of a deeper cosmic truth, then what comes next may define an entire generation of astronomy. For all the limits that currently restrain our view of the early universe, the future is filled with new telescopes, new surveys, and new techniques that promise to push back the veil even further. We stand at the threshold of an era where discoveries once thought impossible. The first stars, the first galaxies, the first black holes, most of them may forever remain unobserved. We detect only the brightest anomalies, the rare moments when cosmic conditions aligned in just the right way. The first step in this journey will be deeper JWST observations. Webb is still in the early stages of its mission, and its capabilities have barely been tapped. Future deep-field surveys will probe even earlier epochs with longer exposures, capturing fainter galaxies and refining spectra from objects like GHZ2. Webb's near-spec instrument can be pushed to its limits, obtaining higher-resolution data that could validate or refute the AGN-like signatures in GHZ2's spectrum. Its MIRI instrument can peer into the mid-infrared, revealing dust heating or subtle radiative imprints that might betray a hidden black hole. Over the coming years, JWST will map the universe at redshifts once considered unreachable, filling in gaps and building a more coherent understanding of cosmic dawn. But JWST alone will not be enough. We will need a coordinated, multi-wavelength effort to detect the hidden population of early black holes that faint infrared data alone cannot expose. Observatories like ALMA will play a crucial role by detecting sub-millimeter emissions from heated dust and gas, offering insights into the environments surrounding early black holes. Radio telescopes such as the Square Kilometer ARA, once operational, will have the sensitivity to detect faint radio cores or jets that could arise from early accretion processes. Even if GHZ2's black hole is heavily obscured,
its gravitational fury may leave subtle signatures in the radio spectrum, signatures we have not yet learned to interpret. The next generation of X-ray telescopes will be especially vital. Missions like Athena, the Advanced Telescope for High-Energy Astrophysics, and the proposed Lynx X-ray Observatory are designed to detect extremely faint, high-redshift X-ray sources. These telescopes will have the sensitivity to detect even heavily buried black holes if they produce the smallest amount of escaping high-energy photons. If GHZ2 truly contains a feeding black hole, future X-ray observatories may be the instruments that confirm it. And if they find similar objects scattered across the early universe, then the hidden population of early black holes will begin to take shape, transforming speculation into evidence.
Beyond these telescopes, new theoretical models will emerge, driven by the need to explain the early universe's apparent hyper-efficiency. Cosmologists will need to refine simulations that incorporate heavy seed formation, rapid gas collapse, and early AGN feedback. These models will help identify the conditions under which early black holes can form and grow, offering predictions that observational campaigns can then test. The interplay between theory and observation will become more dynamic than ever, as each new detection forces simulations to evolve, and each new simulation suggests targets for observation. Perhaps the most compelling future prospect lies in gravitational wave astronomy. As detectors like LIGO, Virgo, and COGRA become more sensitive, and as space-based observatories like LISA, the Laser Interferometer Space Antenna, come online, we may begin detecting mergers of intermediate mass black holes at extreme distances. These gravitational wave signals could reveal the footprints of early black hole seeds merging in the chaotic early universe. A merger between heavy seeds at high redshift would be a direct confirmation of their existence. Gravitational waves, unlike light, are not blocked by dust or gas. They travel through the universe unimpeded, carrying pristine information from epochs completely invisible to telescopes. If the early universe was teeming with black holes, gravitational wave detectors may be the first instruments to hear their distant collisions. All these future possibilities create a sense of profound excitement. The era of cosmic dawn, once thought unreachable, is becoming a frontier we can now explore with increasing clarity. GHZ2 is a signpost pointing toward this frontier, a reminder that the universe still has secrets to reveal. And as our tools improve, we will uncover more galaxies like it, more hints of early black holes, more anomalies that challenge our preconceptions. Each discovery will push us closer to understanding not just what the universe is, but what it was at its most formative, chaotic, and beautiful. But beyond the scientific possibilities lies a deeper, more human reflection. We are witnessing discoveries that reshape the story of everything, not in textbooks, not in theory, but in real time. With each new observation, we peel back another layer of cosmic history, seeing farther back than any humans before us. The future holds the promise of not only detecting early black holes, but understanding the role they played in shaping the cosmos. This is not a closed narrative. It is a living one, unfolding as we watch. And all of this leads us into the final realization, one that carries philosophical weight and cosmic wonder. If the earliest black holes formed almost in tandem with the universe itself, then perhaps darkness was not merely a byproduct of creation. Perhaps it was one of its firstborn elements. In the end, everything we have uncovered, from GHZ2's spectral whispers to the emerging pattern of early cosmic anomalies, leads us back to a single haunting paradox. The universe was born in a blaze of radiant energy, yet its earliest shaping forces may have been forged in darkness. Not darkness as absence, not darkness as metaphor, but darkness as gravity, as collapse, as the silent hunger of black holes forming in the cradle of creation itself. If GHZ2's ancient monster is real, then the universe's first moments were not ruled solely by light, purity, and innocence. They were shaped by two primordial forces rising in tandem, the eruption of starlight and the gravitational pull of newborn voids. Darkness, in this cosmic sense, may not have followed light. It may have emerged alongside it, equal in significance,
fundamental in purpose. This realization unsettles our traditional narrative. We have long imagined the early universe as a place defined by illumination, where the first stars flickered into existence and gradually overpowered the surrounding void. But the evidence hints at a more complex story, a universe in which starlight and black holes co-evolved from the beginning, shaping each other in cycles of creation and consumption. Light brought structure, heat, and complexity. Darkness carved pathways, anchored galaxies, and seeded the foundations of cosmic architecture. Neither acted alone. The cosmos was born through their interplay, through the push and pull of radiance and collapse, through the paradox of energy and absence, co-creating the vast tapestry of galaxies we see today. And there is something deeply poetic, even unsettling, about the idea that the universe's first monsters, these immense, silent engines capable of swallowing light itself, may be older than many of the stars whose light fills our night sky. When we look upward, we think we are witnessing the triumph of illumination, but behind each star lies a history shaped by forces we cannot see. Modern galaxies, bright and orderly, may be the descendants of a much darker, more chaotic phase, where black holes sculpted their growth long before their patterns stabilized into spirals and ellipses. Even the peaceful glow of the Milky Way carries within it the faint gravitational footprint of ancient upheavals. This gives rise to the profound possibility that darkness is not the antagonist of creation, it is one of its authors. Black holes, far from being cosmic anomalies, might be fundamental participants in the universe's earliest construction. They present us with a new interpretation of cosmic genesis, one in which the universe did not simply awaken into light, but into a dynamic equilibrium of light and shadow. In this narrative, the cosmos begins not with a victory of illumination over darkness, but with the intertwining of both forces in shaping everything that followed. Reflecting on this, we are confronted with a humbling truth. When we gaze at the night sky, we are not merely looking at ancient starlight. We are gazing into a universe whose foundations may have been laid by unseen entities, black holes forming in a time when matter itself was still learning how to exist. The earliest chapters of cosmic history, hidden behind fogs of gas and the limitations of our telescopes, may have been dominated by processes we have only begun to imagine. The true nature of the universe may be far stranger than our senses allow us to perceive. And perhaps that is the essence of this revelation, the recognition that our understanding is always incomplete, always limited by the reach of light and the depth of time. The cosmos is vast beyond comprehension, and much of its story lies forever beyond the boundaries of what photons can reveal. Black holes, with their invisible gravity and their silent hunger, embody this truth. They are reminders that the universe is built not only of what we can see, but also of what we cannot. That darkness is not merely a backdrop for creation, but an essential component of it. So as we close this journey, we return to the paradox with which it began. The universe emerged in light, but perhaps its first true giants were born in shadow. GHZ2's faint, ancient whisper may be the echo of a story that challenges everything we thought we knew. A story in which light and darkness arose together, inseparable, intertwined from the beginning. If darkness was truly firstborn, then what we see in the sky is only half the universe's truth. The other half, the half shaped by collapse, gravity, and the silent births of black holes, lies just beyond the edge of visibility, beckoning us toward deeper understanding. And so the story ends not with certainty, but with awe, not with answers, but with the recognition that the cosmos holds mysteries far greater than any single discovery can resolve. GHZ2 is only one hint, one flicker, one ancient clue in a universe that will always outpace our understanding. Yet that is precisely what makes the journey meaningful, the endless pursuit of knowledge in a cosmos where every revelation deepens the mystery. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.